Hi guys, in this first chapter we will talk about a brief history of chemistry, eluding the beginnings of this interesting science and concluding with the experiments performed just before Dalton's atom theory. But before talking about the history of chemistry, we should talk of the meaning of the word chemistry. When you look it up into a dictionary, you will find the following phrase: a science that deals with the composition, structure and properties of substances and with the transformations that they undergo. If you look at the pictures, you have the stereotypic picture of a person performing chemistry, so you have to look very scientific, or something goes terribly wrong until you look like the guy in the second picture. But now, chemistry, what does it do? So, what is the goal of chemistry? Well, the goal of chemistry is to transform some products into new substances. As for example, in this picture, you can see oil in the center that is transformed by chemists into a multitude of substances like, for example, the petrol or the plastics or medicine. That's only a small amount of things that you can do with oil, and that's only an example of what chemists do. But you can understand that chemists transform substances into new substances with new properties. Chemistry was important since the ancient times, and one of the first reactions used was fire. And some chemical phenomena were used even before 1000 before Christ. So once was the extraction of metals of ores, or the fermentation of fruit juices into wine, or even the balsams used to perform mummification. But all of these methods were used without understanding the underlying processes. And then we come to the Greeks. The Greeks were the first to try to explain why chemical reactions occur. That was around 500 before Christ. They divided the substances into 4 basic substances that make up all other substances, and they said that it was fire, water, air and earth. After that separation, they considered the indivisibility of matter, and they were the first to use the term atoms. Atomos meaning what cannot be divided any further. For example, if you take a piece of wood and you cut it in 2 halves and you continue this process, you will end up without nothing or with the last indivisible part of wood, and that would be the atom for the Greeks. And based on this first model, we will introduce in later chapters the particle model of the matter. The first one to make this thought process was Democritus. The next 2000 years were covered by the pseudoscience called alchemy. Alchemy was a magic, mythical based science that even used some obscure symbols to cover up the findings of the science. The alchemists were a closed circle that didn't want that other people could use their knowledge. One of the prime goals of alchemy was to transform metals into gold. That never happened. But in the process they discovered a lot of elements such as mercury, sulfur, antimony and phosphorus, and they also learned to prepare mineral acids. After this somewhat mystical period, in the 6th century the foundations of modern chemistry were laid. Georg Bauer wrote a book about industrial extractions of metals from ores, and some of his processes are even used on a bigger scale until today. Another pillar of the modern chemistry were the work of Paracelsus, who was the first to use some substances as medicine. And he has one famous quote saying, "Poison is in everything and no thing is without poison. The dosage makes it either a poison or a remedy." And then we come to Robert Boyle, who performed for the first time quantitative experiments concerning gases. He also wrote a very famous book, The Skeptical Chemist, which is the foundation of the modern chemistry books, because he introduced a quantitative concept in chemistry and physics. Furthermore, Boyle defined an element as a substance that cannot be divided any further, and he was the father of a constant growing list of known elements. And then, unfortunately, we come to some dead end in modern chemistry, because in the 17th and 18th centuries, combustion was in the center of interest. And combustion was explained, as you can see it in the first picture, with phlogiston, a substance that was explained to come out of the substances that are burned. If a metal like iron is burned, it becomes heavier, and that is in contradiction to the phlogiston theory. So the theory was a dead end for nearly 2 centuries for the science known as chemistry. But the study of combustion continued on gases like CO2, N2, H2 and O2 that were discovered during this so-called dead end. And then we come to the father of modern chemistry. Antoine Lavoisier was the first to understand and to explain the true nature of combustion. His experiments suggested that during a reaction, mass is neither created nor destroyed. He formulated the law of conservation of mass. So he understood that combustion involves the fixation of the gas oxygen when you, for example, when you burn a metal. Also, he was the author of a very famous chemistry book, the Traité of Chimie Élémentaire, and unfortunately he died by the guillotine during the French Revolution. Inspired by Lavoisier's work, other chemists continued to perform experiments involving precise measurements of masses. Joseph Proust discovered, for example, that a given compound always contains exactly the same proportions of elements by mass. This is known as the law of definite proportion. This law causes a lot of difficulties for new students in the branch of chemistry, so we will explain it later. But for example, if you take the substance copper carbonate, it always contains 5.3 parts of copper to 4 parts of oxygen to 1 part of carbon by mass. So I think that you can understand this sentence, but it is better explained with a concrete example. For example, if you want to make a cake, you take 120 grams of butter, you take some flour, you take milk and you take eggs in certain quantities of masses. So the cake will weigh approximately what the different comparts of the cake weigh. And then if you perform a percent calculation of the quantity involved in the total of mass, you find a certain number that is constant. For example, you took 115 gram eggs and the whole cake weighs 620 grams. You perform a division and you multiply by 100 to get percent value. You find that the eggs always make up 24.2% of the cake. And that will be true for every cake you make with these basic ingredients. That is the law of definite proportion. This proportion never changes. Even if you take, for example, 2 cakes, you have the double of mass of the cakes, but you also have to double the mass of the eggs. So the percent proportion will be the same. The proportion in mass stays the same for the component cake. And that is true for chemical compounds. They always have the same distribution percentage of mass. That's the law of definite proportion. For example, if you take it in chemistry, take this reflection into chemistry, you have a bottle of water. Inside you have water. And the water molecule H2O always contains 88% of oxygen and 12% of hydrogen. It doesn't matter which water you take, this will always be a constant. This is the law of definite proportion. For example, if you take tap water, it's also H2O containing the same percentage of hydrogen and oxygen. And this law even has implications on a wider scale. For example, if you are willing to make lead sulfide, inside this compound you always find lead and sulfur, and always in constant proportions. That 10 grams of lead always react with exactly 1.55 gram of lead to produce 1.55 gram of lead sulfide. These are the constant proportions that never change. So even if you take more sulfur, it won't react with the lead that you are willing to take. So you will have leftovers. That's another proof of the law of the definite proportion, because you can't react more sulfur than as it is preseen by the law of the definite proportion. These discoveries stimulated John Dalton, another great chemist, to think about atoms and to develop a model that we'll explain in a later chapter. His reasoning was founded on an observation, because he reasoned that if compounds are composed of tiny particles, they should always contain the same combination of these atoms. And he made an interesting finding. There are certain substances that combine to form different substances, like NO. NO, for example, the element N and the element O can combine to form different substances like NO, NO2, N2O, N2O4 and N2O5. But Dalton found something interesting. If you take 1 gram of N and you look up how much O can combine with this 1 gram of N, you find that you have different possibilities. 1 gram N can combine with 1.04 grams of O, and so on. So the quantity of O changes that combines with 1 gram of N. But here is the interesting fact. The ratios of the masses of the second element that combine with 1 gram of the first element can always be reduced to small whole numbers. Meaning that if you divide through the smallest ON mass ratio, that is 0.578, you find always whole numbers. This finding, that will be explained in more detail later, further convinces him of the existence of atoms and stimulates him to develop a rather complete model of the atom that will only be changed later by findings that could not be explained by his model.